In this brief video, I will show how to use a contingency table instead of a tree diagram for one of the examples in our textbook. The example we will look at is example 3.42 in section 3.2 of the text. For that problem, we are given the following information. We are told that in Canada, about 35/100% of women over 40 will develop breast cancer in any given year. That is, the probability that a woman over 40 has breast cancer is equal to 35/10,000ths, where I've converted the percentage into a decimal value. Note that this also implies that the probability of a woman over 40 not having breast cancer in any given year would be 1 minus the above value. That is 9,965/10,000ths. We are also told in about 11% of patients with breast cancer, the test gives a false negative. That is to say that the probability that the mammogram has a negative test result, given that the woman has breast cancer, happens about 11/100ths of the time, 11% of the time. We are also told in about 7% of patients who do not have breast cancer, the test gives a false positive. That is, the probability of getting a positive mammogram result, given that the woman does not have breast cancer, happens 7 out of 100 times, or 7/100ths. So here's the question that is asked in example 3.42. If we tested a random woman over 40 for breast cancer using a mammogram and the test came back positive, what is the probability that the patient actually has breast cancer? In other words, we want to know the probability that the woman over 40 has breast cancer, given that she had a positive mammogram result. Now, we can use the formula for finding a conditional probability that is given in the book. And notice that that means we are really looking for the probability that a woman over 40 has breast cancer and she received a positive mammogram result, divided by the probability of a woman receiving a positive mammogram result. So to find the probability that we are looking for, which is on the left of the equal sign, we're going to focus on finding the pieces on the right of the equal sign by using a contingency table. So here's the contingency table we're going to use. We're going to set up a table that has mammogram results in the columns, either positive or negative, and the truth of whether the woman has cancer or not on the rows. So to find the probability that a woman over 40 has breast cancer and has a positive mammogram result is going to correspond to finding the value for the cell that is identified in the contingency table below in red. To find the denominator, the probability that we have a positive mammogram result, is going to involve finding the total of the column values that are labeled positive, which I have shown in the red box of the table below. Really what we're looking for is the column total for the positive mammogram results. Note that we can also identify what the probabilities for the remaining 2 cells of the table should be, and I've shown those in red. The probability that a woman has breast cancer and a negative mammogram result, and the probability that a woman does not have breast cancer and also has a negative mammogram result. So we're now ready to use the given information to begin filling in the cells of our contingency table. Let's look at what we're given again. So we're given the probability that a woman over 40 has breast cancer, and we saw that it also implied that we can find the probability that a woman over 40 does not have breast cancer. We also know the probability that if a mammogram result being negative, given that a woman has breast cancer, was 11% or 11/100ths. And we also saw that we were given that a mammogram result being positive, given that a woman doesn't have breast cancer, was 7% or 7/100ths. But how do we find the probability that a woman has breast cancer and a negative mammogram result? Well, it turns out that's fairly straightforward using our formula for joint probability. We would need to find the probability that the woman has breast cancer, timesing that by the probability that she has a negative mammogram result given that she has breast cancer. And we have those values from the previous given information. That's going to be 35 10,000ths times 11 hundredths, which gives us a value of 38 100,000ths for that probability that she has breast cancer and a negative mammogram result. We also want to find the probability of the woman not having breast cancer and having a positive mammogram result. Fortunately, we can use the given information from the previous page, the previous slide, and our formula for a joint probability. That's the same as finding the probability that a woman doesn't have breast cancer, and we're going to multiply that by the probability that we have a positive mammogram result given that the woman has no breast cancer. So that conditional probability. We have those values from the previous slide. That would be 9,965 10,000ths times 7 hundredths, which gives us a result of 6,976 100,000ths for that probability. We're now going to take these two values that we just found, and we're going to plug those into our contingency table. So on this page, you can see that I've taken those values and I've plugged them into the appropriate places in the contingency table. You can see those in red below. Now, given that we now have some values that we need, can we find this last value that we need in order to calculate the probability we want? All we need to now find is the probability that a woman has breast cancer, a woman over 40 has breast cancer, and a positive mammogram result. Well, fortunately, we know the total of this particular row of whether a woman has cancer. And I'm going to go ahead and show that on the next slide. Notice that the row total must equal 35 10,000ths. That's the percentage of women over 40 that have breast cancer. So we can go ahead and use that value, subtract off the 38 10,000ths that is in the row for a woman having cancer and having a negative mammogram result, and we get 312 100,000ths for the probability that a woman has breast cancer and a positive mammogram result. And notice that we now have all the values we need inside this red box, and we can now go back and calculate these two values to get our probability for whether a woman over 40 has breast cancer given that she had a positive mammogram result. Okay, so let's go to the next slide and take a peek at that. So here's the work that I did for finding the probability we're looking for. So the probability that a woman has breast cancer and a positive mammogram result is given by the 312 10,000 or 100,000ths, excuse me, that we calculated earlier. And then I'm going to divide that by the total of this column for a positive mammogram result. And when I do that, I get a value, a final probability value of 428 10,000ths approximately for the probability that we were looking for at the beginning. Notice that that says that a woman has approximately a 4% chance that a woman over 40 who has breast cancer gets a given that she got a, okay, let me say that again. So that's the probability that a woman over 40 has breast cancer given that she had a positive mammogram result. It's just a little over 4%. And that concludes this presentation. I hope you have found it helpful.